Hello. The final chapter of this topic is called hypothesis testing. It is a bit of a step up in complexity from the previous stuff, and it kind of is repeated a lot in year 2, so you'll see this idea quite a lot moving forwards. The idea of hypothesis testing is that you test an idea, someone's claim, to decide whether or not it's too unlikely. And if it's too unlikely, we're going to say we don't quite believe you. We're going to leave maths aside for a little bit and have a look at how we do this process in real life without even thinking about it. So here is my claim. On my way to college, I saw a person who was over 5'9" tall. Now, usually I do this with classes so I can get a score of how many people believe this. But have a think to yourself, would you believe this as a statement? So I walked to college, I walked through all the people coming off the buses. Would I see someone over 5'9" tall? The answer is probably. So this is quite believable as a hypothesis. As we go though, if I increase this height, 6 foot tall, you'd probably believe that. There are plenty of people, you might even be over 6 foot yourself, but there are plenty of people over 6 foot tall. So this, probably believable. The next couple get steadily more ridiculous. So 5'3", 5'6", 5'9". At some point you're going to stop believing this statement because it becomes more and more and more unlikely to a stage internally where you're like, no, you didn't see someone who was over 5'9" tall. So have a quick think to yourself, would you have stopped at 6'6" or 6'9"? Would you still believe it at 6'9"? 6'9" is a very, very tall person. So we've got this idea for hypothesis testing of eventually what we're doing is we're trying a hypothesis, an idea, against how likely it is. In real life we do this all the time. We might call people out on claims. You might say, no, the fish was not that big that you caught. Fish don't get to be that big. But yes, we're going to have a look at how we do this as a mathematical process. We could also have a look at it a slightly different way. Here's another statement. On the way to college, I saw a yellow car. So I walk along the dual carriageway up from town, so you can probably see a few yellow cars maybe on there. I saw 2 yellow cars. Is this believable? I saw n yellow cars. How big would n have to be for you not to believe me? So there's a couple of terms that we have to define here in order to make sure that we're all talking about the same thing. So I'd ask you to pause the video after we've gone through these just to make sure you add all of these to your notes, because you do need to still be taking effective notes. So a hypothesis is about any statement about a population parameter, usually a probability. So this might be about a mean, it might be about a probability, it might be about some kind of statement, a parameter about the population. It might be a percentage, proportion, something like that. A test statistic is anything we can measure and do some calculations. So it might be the number of 6s, it might be the number of people with a disease. Our null hypothesis is a commonly accepted true statement. It's things like coins are fair, dice are not biased. So it's always in the form probability equals or proportion equals, and this is something that we can do calculations assuming that this is true. Our alternative hypothesis is what we're going to accept if the hypothesis is wrong. The null hypothesis is wrong. So this might be the probability is not equal to, it might be the probability is greater than something, or the probability is less than something. So we've got 4 bits here which basically set up a hypothesis test. So I'm going to give you a little bit of time to add these to your notes. Pause the video if you want. So here we have our first in context example. So John here wants to see if a coin is unbiased or whether or not the coin is biased towards coming down on heads. He tosses the coin 8 times and counts the number of heads. From a non-mathematical point of view, if I tell you a coin is biased or unbiased, and then I toss the coin and it comes out on heads 8 times, that's going to be a biased coin, right? The chance of getting 8 heads is remote. Maybe 7 heads as well, you'd be suspicious. What about 6? This is why we need a mathematical test to try and decide whether or not 6 is unrealistic. How likely is 6 heads? So we're going to be using binomial, because that's what a probability model where we have something repeated a set number of times with a constant probability of success. So our test statistic is x is modeled by a binomial distribution, and we're tossing this 8 times, and we'd expect a probability of a half each time. So x is a binomial. Remember, this is n and this is p. So this is our test statistic. We might also want to make a note that x is the number of heads. So, a suitable null hypothesis. Well, we don't know what the probabilities are for a biased coin, because it might be 0.6 for a head, it might be 0.8 for a head. So our null hypothesis, H0, is going to be coin unbiased, P equals 0.5. Some people, instead of putting this 0.5 in here, would just put P, and then we've got P in here. So you could put P here, you could put 0.5 up there. So this is the coin is fair. And our alternative, H1, because we're after bias towards coming down on heads, we want the probability of a head to be greater than 0.5. So the coin here would be biased towards heads. I really like putting a little bit here about what my hypothesis test actually, or the hypothesis in this case actually means. So our null hypothesis H0 is our coin is fair, and the alternative we're willing to accept is it's biased towards heads. Nowhere in here have we got the possibility that our coin might be biased towards tails. So we're not looking for the possibility that the probability of getting head is less than 0.5. So what we'd need to do now, if this was an actual hypothesis test question, is to do a calculation and find out how unlikely these upper probabilities are. How unlikely is 8 heads? How unlikely is 7 heads? And we can see which ones we'll reject. We're going to do a little bit of extra here and have a look at what this, whether this would go. So if I go on binomial distribution, go on normal PD, which is 4, variable. If we do 8 heads out of 8 with a probability of 0.5, we can see this is already in standard form. If you're ever not sure about this, just do +1. I can't do +1 in this mode. But yes, this is already way smaller than we'd like to accept. What we need to do is to come up with some idea of how small does it need to be before we start rejecting ideas. So clearly if we get 8 heads, the probability this is tiny, we're going to say we don't believe H0, it's a fair coin. We're going to assume instead it's H1, this coin is biased towards heads. There are some more definitions we have to do before we go any further. We've got the idea of one-tail and two-tail tests. The idea for this is sometimes we have one possible option. Like in the previous one, we were just looking for coins biased towards heads. So anything where we have one possible option, this one up here is called a one-tail test. So here we've got probability is less than, probability is greater than is one-tail test. Because we're only interested in one other possibility. It might be equals a half and probability of greater than a half. Or alternatively probability of less than a half. And you only have one of these two things, that's why it's called a one-tail test. There's another way of doing it. You could have a not equal to, where we're keeping open the probability of having a one-tail test, so probability of having a greater than or a less than, and we're going to have two different possibilities for what's our alternative hypothesis. So to carry out this, we're going to do a probability calculation based on a null hypothesis being true. So when we had a look at this one here that we just did, we did a calculation based on the coin being fair to see if that was unlikely or not. We've got this threshold here called significance, where we're going to say we don't believe the null hypothesis if it's less than maybe 10% or 5% or 1%. Now 10% is actually quite a high level of significance, and 1% is actually quite low. Things that happen 1%, 1 out of 100, are quite rare. And basically what we're saying is if the chance of this happening with our null hypothesis is less than this, we're going to throw away the null hypothesis and say we don't believe the null hypothesis is true, and we're going to accept our alternative instead. This will take a little while to see how it works. We're going to have a quick look at a graph first just to see how this kind of thing works. So if we have a binomial probability of n is 20 and p is 0.5, I've got a piece of software called GeoGebra to draw out some graphs of how big each of the probabilities are. And we can see the probabilities of 1 and 2 and 3 are absolutely tiny. Once we start to get to 4, 5, 6, we actually get meaningful probabilities. Chance of doing 20 dice and getting no heads is pretty much 0. If we were to do a one-tail test, and we were doing less than, so this bit down here, if our 5% is our level of significance, here if we do 0 to 5, this is 2%, and if we do 0 to 6, we get 5.77%. The ones that we're going to reject are anything between 0 and 5, because this is the bottom outcomes that are less than 5%. So we're not testing probabilities here, we're actually testing a tail, which is this idea of this thing and everything more extreme than it. So you could have a tail going this way. Obviously this is a hump shape and then there's a tail going off the other way, but we weren't interested in that because this is a one-tail test. So this idea of this thing, 5 and everything less than it, is 2%. So anything in here, we would say it's too unlikely, we're going to reject H0. This one here got up to 5.77%, so 6 is acceptable. Because this thing and higher is bigger than 5%, 6 does not lie in the 5% of least likely outcomes. And this is something that's quite hard to get to grips with at the start. We're going to be doing hypothesis tests probably for the next 2 lessons until we've got to grips with it. But it is quite new at the start. Okay, another question in context. You'll probably notice that these questions get quite wordy, and most of the words on here are important, so we do need to read this carefully. So an election candidate believes they have the support of 40% of the residents in a particular town. So this is actually a probability even though it's written as a percentage. It wants to test at the 5% significance level, so we're after this, is the chance of this bigger than 5%? Whether the candidate is overestimating the support. They ask 20 people, 3 say that they do. Okay, so write down a suitable test statistic. So because they're testing 20 people, we're going to say X is the number of support members, and X is modeled by a binomial 20, P, whatever probability we choose to use. So this is for A. We could fill in our 0.4 straight away because we know that's the probability we're going to use. Write down 2 suitable hypotheses. So for B, our null hypothesis, we're going to use this idea of 40% support. So H0, this is P equals 0.4, so this is 40% support. And H1, this is going to be the probability. We want to know here if they are overestimating their support. If they're overestimating their support, we suggest that the probability is less than 0.4 because they are overestimating it up to 0.4. So this is less than. %40 support. So these are our hypotheses. Either it's a 40% support. The alternative we're willing to accept is it's less than 40%. This is one tail. Because there's only one possible option. We're not entertaining the probability that his support or her support might be more than 40%. Okay, for C, explain the condition under which the null hypothesis would be rejected. So here we have 3 people say that they do. So for C, we're going to reject H0 if the probability that X is less than or equal to 3 is less than 5%. So if you go back to our graphs over here, remember we're always testing this and less than to see if it's bigger than the significance. Alternatively, if it's on the other side, we're doing this and greater than, because this is like a symmetrical shape. So we are testing if 3 or greater, because in the question they gave us 3 people, that's our result. So 3 or less, is that bigger or smaller than 5%? And because we've got all this information, we could actually do it. The question doesn't ask us to do it, but we're going to have a quick look and see if this would be. So we're going to go on distribution mode, and we're going to go on binomial CD, which is option number 1, variable. We're going to enter 3, 20, and 0.4. So this probability actually comes out to 0.15160. So actually this is less than 5%. So with the information we've got, we would conclude not that they have 40% support, but their chance of getting 3 out of 20 with 40% support is so unlikely, we're going to go instead with this 0.4. Less than 0.4, our alternative hypothesis. So we didn't have to do the calculation in this question, but it's useful to see where we're going with all of this. Okay, we're now going to have a go at exercise 7a on page 100. I suggest not doing question 1 because question 1 is just about restating definitions. This is one of the few topics in stats where 2 or 3 minutes into the lesson everyone is turning around going, I have no idea what to do. There's a lot of new words, there's a lot of new definitions. I'd suggest having your notes open so that you can have a look. But I'm actually going to, if you pause the video and have a go at the questions, but I'm going to go through questions 2, 3 and 4 just to try and help you get to grips with this. So if you are struggling with questions 2, 3 and 4, have a go at them, have a look at my video solution for them, and then you can have a go at the rest of the exercise. Okay, question 2. Have a go at this first, but then we're going to have a quick look at it. For each of these tests, state whether or not they are one-tailed or two-tailed test. So this is about how many different options do we have for our alternative hypothesis. So for this one, there's only one option, which is probability is greater than 0.8. So this is one tail. This one here, again, is less than 0.2. This is one tail as well. This one, however, not equal to 0.6. This is two tail. Because here we would have the option, the probability could be less than 0.6 or greater than 0.6. So this has two options, 0.6 and greater than 0.6. Whereas these ones only have one option, and it's the option given in the question. For question 3, we have Dimitri and his dice. So he wants to find out if it's biased towards the value 6. So he throws the dice 60 times, determine a test statistic. So this is going to be x is modelled by a binomial 60, because that's how many times he throws it. What's the probability of getting a 6? Well, it's a sixth, if it's a fair dice. You could, if you want, write x is modelled by a binomial 60, p, and then later on define what p is. Some people like doing it this way, some people will just put the sixth in straight away. So write down a suitable null hypothesis, H0. Well, we don't know how to do calculations with a biased coin or biased dice. So the one that we can do calculations with is the fair dice. So p equals 1/6. So this is fair dice, or die, or dice. In the question they've gone with dice, so we'll go with a dice. H1, we've got p is greater than 1/6, so this is bigger than 6, more likely to land on 6, biased towards the value of 6. This is a one-tail test. It doesn't ask us whether it's a one-tail test or not, but we can pick out one possible option. It's a one-tail test. If it had taken out the word towards the value 6 in here and just said biased dice, we'd have to do not equal to 1/6. It would then become a two-tail test because it could be biased towards 6, it could be biased away from 6. Okay, we've got one of these explain why such and such has made a mistake. So we need to read the question very carefully and work out what's going on. She wants to do a test to see if a coin is biased. Because it's not said positive or negative, if it's not said biased towards heads, we're probably going to be doing a two-tail test here. So she tosses the coin 100 times and counts the number of heads she gets. Shelley says that her test statistic is the probability of it landing on heads. Now you can't test probabilities. You might think you can, but you don't get actually a probability if you flip it a number of times, because it might not be exactly the same as the probabilities would suggest. If you toss a coin twice, you're not always going to get one head, one tail. So that won't give you something that you can actually test. You can't test a probability. So explain the mistake she's made and correct the test statistics. So for A, let me find a pen that's a bit better. Our test statistic is x is modelled by a binomial. It's 100 times and 0.5, or p, and then we need to define what p is. So this is our test statistic. But the mistake she's made is that probability can't be measured. So you can't truly measure probability of a coin. So you can do an experiment, but it's not guaranteed to fit with that probability. If it's probability a half, you're not guaranteed to get 50 heads and 50 tails, because that's how probability works. It only gives us a chance of getting a head. It doesn't actually give us the number of heads. So a test statistic needs to be something we can measure. So this is number of heads. And we can't actually measure probability. Write down a suitable null hypothesis. So for B, we're going with H0, P equals 0.5, which is fair coin. Write down a suitable alternative hypothesis for C. This is H1, probability is not equal to 0.5, which is a biased coin. You'll notice this is actually a two-tail test, because there are two possible outcomes. It could be greater than 0.5, it could be less than 0.5, it could be biased towards heads, or biased away from heads, or biased towards tails. I suggest having a go at some of the rest of these questions. We're going to have a look at hypothesis testing a lot more in the next two lessons, and really get to grips with how you do a hypothesis test. So this first exercise is about, can you pick out one tail or two tail? Can you pick out your hypotheses? And can you work out what a suitable test statistic is?